One thing I love about software is weird approaches that at one point were basically common knowledge, but then as tech changes, as best practices differ, they may not necessarily be better, a lot of these ideas are just forgotten to the sands of time, and this blog post opens with a really good example of that. The magic of software, or what makes a good engineer, also makes a good engineering organization. This was written about a year ago, but frankly, even if it came out 20 years ago, nothing would change except for the examples. It is a very timeless piece. The people who create software generally refer to themselves as software engineers, and yet if they graduate from university, it is typically with a degree in computer science. Now, I'm one of the rare exceptions that actually does have a software engineering degree. Yes, I do have a degree. Yes, I'm one of those people who got a degree and then made YouTube videos. I know, haha, laugh about it in the comment section. But most people, this is the route they go. That has always felt a little strange to me because science and engineering are two pretty different disciplines, yet we for the most part seem to take an obvious contradiction for granted. However, I think there is something uniquely magical about software, and part of that magic might stem from this tension in how we define it. At first glance, software seems like a straightforward engineering practice. After all, it exists within a fully known universe, the computer of our own making. Take, for example, engineering a bridge. If you know how to build a bridge, you understand the theory of how to build a bridge. Building a bridge is not difficult. The difficult part is the fact that it exists in the real world where things you don't control can go wrong. There can be an earthquake, there can be heavy rain, there can be some issue that was not really discovered under the ground, there's a sinkhole in that area, things that you just don't have control over. If you're doing so in a fully defined world, the problem is considerably easier. This is in stark contrast to disciplines that are more obviously science, like biology and physics, which exist within domains that we did not create and do not fully understand. Unlike computers, which are fully understood, maybe not by most people, but the idea of how a computer works, how to build a computer, how a computer functions, all of that is a well-defined problem space. Those disciplines are in large part about the search for understanding. Science, in other words, is often occupied with the process of discovering how something works, which we don't need to do with computers. Instead, what we're doing is working out how to use this computer to complete various different tasks. We understand the constraint of the system and are trying to use the system to achieve a goal. Or said in a more eloquent way, with nothing to discover, we might say that software is the engineering practice of combining and assembling what is available from the complex system of computing in order to manifest a given vision. However, vision and engineering aren't necessarily two separate ideas. When we're talking about software, they kind of merge together, they're intertwined, where your vision inspires the engineering, and the engineering inspires the vision. You work out that something is possible, and this gives you an idea of something you might want to do. Consider these two animations, especially the one on the right. This is still gorgeous. This is an ancient animation, and yes, if you stare at it long enough, you're gonna notice, oh, the water's not the most realistic water. Oh, there's some color palette limitations, all of these little things where, yeah, it is showing its age, but it's still a gorgeous piece. The thing is, though, neither of these animations, when they were first made, were animated in a way that you would typically think of animation. These aren't individual frames that were drawn and then sequenced together. That's not how this works at all. And whilst it's totally possible to do now, considering the hardware at the time when these were made, you wouldn't have been able to get a fluid animation doing that. It just would not have worked. So instead, this is a complete software trick. These were actually images made using a technique known as color cycling. Color cycling exploited the fact that graphic systems like VGA used indexed color. Indexed color systems were a memory optimization technique for representing each pixel on the screen with a single byte color value rather than a full 3-byte color value, along with a separate color palette that mapped these 1-byte values to a full 3-byte RGB value. So you have a color palette here with each of the colors you are using, and then each pixel is given an index in that palette rather than the color itself. Now, you might not know the name of the technique, but you've probably seen seen it. This was really common in SimCity 2000 to animate buildings. This was used on the Windows 9X series, so 95 and 98, for the animation on the boot screen. This was used in Sega Genesis games like Mickey Mania, and was common in adventure games in the 90s to animate water, lava, other things with a repeating animation. One thing I really disagree with the author on is impressive for the time. I think these are still impressive to this day. Not because they're the most AAA, amazing $10, $20 million animation budget. Not because they use the craziest effects, but because the people who made them understood framing, understood animation, understood art, and they weren't just programmers. Things like this are made by people who would have made something amazing in any era. Give them the tools of today, and they would still make something amazing. Give them the tools of 100 years ago, and they would do exactly the same. These are people that aren't limited by their tools. They embrace limitations and work within them. And using tricks like this is how you get the Amiga Boing demo. This is not a 3D model. It is entirely made using this animation hack. I think this was a somewhat non-obvious result. Index color systems weren't created for this purpose, but software developers who understood them were able to use them to create something unexpectedly great. Computing in general is a long history of non-obvious results. I mean, if I'd been there at the beginning of it all, I'm not sure I would have predicted that by quickly turning electricity on and off, we could get all of this. Somehow we managed to trick rocks into thinking. Much like with pure science disciplines, software history has been a history of discovery. However, while understanding is the object of discovery in biology and physics, understanding in engineering is often the basis for discovery in software. While software development is indeed the process of combining and assembling resources to manifest a given vision, deep understanding of the resources and all the ways to use them also inform the vision in a bidirectional manner. It is not always as simple as starting with a vision and then using the resources available to build it. They often merge together or in an intertwined way, and things continually leap forward over and over. If we consider the animations above to be a software product, it is clear that the product did not begin with a vision that someone had for animations which looked this way. It was an understanding of the engineering that informed the vision, and vice versa. The people that made these animations would have made amazing animations if this didn't exist, if there was no way to animate in this way. But this did exist, there was a way to do it, and they made use of it. Now, color cycling is a good example because it's visual and so old as to be uncontroversial, but it's a pattern that I've seen appear again and again throughout the course of my involvement with software. Deep understanding of tools and technology yields a new vision, unexpected results, insight, or a solution of some kind, big or small. That doesn't always mean a new product or demo, and more often than not is simply an advance within a project that only a small group of people will ever take note of. But it almost always starts with the understanding part. I feel like we might be losing sight of the understanding part. Abstractions. Building more, creating less. In software, we benefit from abstraction layers. If you want to save data to your drive, you don't need to write a way to do that every single time. There are low-level libraries that will go and do so for you. And then there are libraries built on top of those libraries that make those libraries more convenient to use. And then there are game engines built around that, and you can use that for save data. But the game engines are also built on top of graphics libraries, which are then built on top of the lower-level drivers, which control the hardware. And all of the software running on your system is this giant stack upon a giant stack upon a giant stack, all running on top of the kernel. There is so much stuff running on your system that you don't ever have to think about unless you actually want to think about it. And in many cases, this is a good thing, right? Like, I don't want to have to control my GPU just to be able to have some sort of graphics on my screen, have a basic environment. This is a good thing, but it can go too far, especially when it gets too close to the creative process. There are two ways of interacting with an abstraction layer: as a shorthand for an understanding of what it is doing on your behalf, or as a black box. And for most of your system, it's going to be a black box as opposed to something you understand, but you just don't want to deal with right now. I think engineers are most capable and most effective when abstraction layers serve as a shorthand rather than a black box. Computing is so complex that these interfaces are never perfectly clean and never will be. So to use them as a black box without understanding what happens within them can lead to negative outcomes, which compound with the size and complexity and scale of the application. Now that doesn't mean that you have to understand every little possible thing about your system. No one has the time to do that, especially with modern systems, which are as complex as they are, but you should understand the things within your problem domain. For instance, sometimes we create abstraction layers that allow people to create things on top of them without explicitly having to understand anything beneath them. We call those platforms. I think we can go to like a really high level here and talk about something like a Squarespace, for example, a drag and drop site creator. You don't need to even understand basic JavaScript, CSS, any HTML whatsoever. At least at a basic level, using one of those systems, you can just put a thing in there. You can probably click a thing and it applies some action to it. It's doing all of this stuff in the background, and you have no idea how any of it works. And the expectation is that when we create abstraction layers like that, we should see an explosion of creativity, since now people can focus only on the creative aspects of what to build, rather than the technical aspects of how to build it. And this seems obviously true for some endeavors. Take, for example, filmmaking. Most people who are making a movie, who are shooting video, or anything of this sort, if you handed them the pieces of a camera and said, build, most people have no idea how to build a camera. Now, they might understand some technical aspects of how a camera works, how lighting affects the lens, different lens types, and all of this stuff that actually affects the creative process, but they have no idea how a camera works at a fundamental level, and they don't need to, because that doesn't actually affect them. And we can say the same thing about painting. Most people have no idea how their paint is actually made. If you took them to a paint factory, they might be interested, but knowing how paint is created doesn't necessarily affect the painting process. And we may be tempted to extrapolate from this into the world of computing and say that by creating something like a game engine, we should expect to see an explosion of creativity in games, because now game makers can focus on the creative aspects of building games without having to understand the technical aspects of how to build a game, in the same way that a filmmaker doesn't have to build a camera. However, I think the problem with metaphors like these is that a camera is not actually an abstraction layer for a film. A story does not simply sit on top of a camera. A camera is never going to make a movie by itself. There is a lot of other really complicated stuff that a filmmaker really does have to understand about making a film that is necessary in order to bring a story to life. And when we apply this same logic to computing, you do see a lot more stuff, right? Steam has more releases than ever, but when we see the number of incredible releases, that doesn't seem to change with the access to better software. Now, that doesn't mean that easy-to-use game engines benefit no one, but it's not a proportional relationship. Some people are going to be brought up, but those people are the outliers. Just because you have 1,000% more games doesn't mean you're going to have 1,000% more amazing games. To me, in complex ecosystems like computing, there just seems to be some kind of ongoing relationship between deep understanding of how tools are used to create things function and the quality or creativity of the output we get as a result. Put in another way, if you're going to create something amazing, you need to have a deep understanding of your problem space. As a game developer, you don't necessarily need to know how bits are arranged on your drive, or how powering a rock on and off makes it do computing things. Like a filmmaker doesn't need to understand how the internals of a camera work, but you do need to understand the things that are relevant to your problem space. When teams become Tupperware, sealed tight and stale inside, I think this applies in all kinds of meta ways to the software industry as a whole. For instance, I think many of the dynamics that make a good engineer are also the dynamics that make a good engineering organization. Engineering organizations have ballooned to huge numbers of people. Look at any single AAA game developer and explain to me why you need that many people working on a game. And these huge engineering organizations don't exactly have a reputation for high velocity output. I would say, or in some cases, high quality output, but that's a separate discussion. Some of this is the result of what happens with products at scale. It is fundamentally faster and easier to iterate, improve, or change a product with 100 users than it is to do with 100 million users. However, having seen inside some large engineering organizations, I don't think that explains everything. Most people managing or building engineering teams today have a familiar management philosophy, the general thesis being that hierarchical decision-making, where information flows upwards in the forms of reports, summaries, and executive summaries, and then flows back downwards in the form of budgets, headcount, and priorities, too slow, doesn't work with a big team. It might work with a small organization, but if you're dealing with an organization of 500 people, nothing's ever gonna get done. So instead, what they do is operate as these semi-independent autonomous teams. The problem is they don't tend to operate autonomously. And this is similar to how people think about vision and engineering, where one leads into the other, and it doesn't really leave room for a bi-directional relationship that is going to emerge, where the engineering can once again feed back into that vision. To exacerbate this, organizing engineers into silos is very similar to creating abstraction layers for an organization, almost like a microservices architecture. Unfortunately, these abstractions are almost always treated as black boxes, both by peer teams and by leadership teams. They are treated as a thing where you say, here's a task to be done, you don't care how the task is being done, you don't know how the task is being done, it just gives you an output. And much like in software, living in a world of black box abstractions can make it difficult for anyone to have insights that are necessary for truly excellent outcomes. It is a great way to make completely functional software, mediocre software, where it's fine. No one's gonna maybe someone's gonna complain about it, but it's not gonna be utter garbage. But it's not going to be amazing. A thought experiment I like to apply to an engineering organization when considering its efficacy is to imagine that it is Skype at the dawn of mobile. Imagine that you're running Skype, that you have all of these people siloed into autonomous teams, and you have the foresight to see how important mobile is going to be. So you make sure that everyone is aligned on mobile as the key, number one, absolutely existential priority for the organization. Even with everyone aligned, adapting to mobile is a big lift. The existing product is 100% organized at every level around a desktop model. The UX is centered around the concept of being online or offline, which no longer exists in a mobile environment. The communication protocol is a semi-distributed mesh that is dependent on being able to run in the background on a desktop OS, which won't work on a mobile device. The codebase is written in a way that is not deployable on mobile OSs, so on and so forth. Clearly, things need to change. Everything needs to change. But the change that every team needs to make is dependent on the change that every other team needs to make. The product vision itself is intertwined and bidirectionally informed from the engineering. And if everyone in the organization sees every other part of the organization as a black box abstraction layer, I don't think a change like that is going to happen. So even though these are supposed to be these autonomous teams, they're all interlinked together and all of their work is directly connected to each other. While seismic shifts like the mobile revolution may seem rare, I think organizations ill-equipped for radical change are likely underperforming even in stable times. Just like with software, where deep understanding is often the basis for discovery, an organization has to truly understand itself to be primed for innovation. When teams operate as impenetrable black boxes, vision becomes myopic, and potential withers. I think the problem is too many people have a vision. There are too many cooks in the kitchen, and they will begin to diverge. Truth loops and false idols. I've noticed that aspiring entrepreneurs often fixate on studying the current habits of successful entrepreneurs, hoping to mimic their achievements. We've all seen the people that dress like Steve Jobs. We've all seen the people that wake up at 5 a.m. and think that is the thing that is going to make their life amazing. And maybe a more engineering-focused example, we've all seen the engineers who are learning the newest, hottest toolkit that everyone's going to forget about after 5 minutes and go back to jQuery and React. I think there is a similar fallacy for how we consider engineering organizations. Many of today's best practices have been drawn from long-established internet companies like Google, especially with how they lay out their offices. However, the problem with copying their current practices on the basis of their success is that most of those companies found near invincible business models that basically printed money. It was not the fact that they are organized the way they are that made the money, it's the thing they produced that made the money. Without much in the way of selective pressure, I think the practices and cultures that are developed at these companies more often reflect optimizations for the benefit of various decision makers, rather than optimizations for actually creating something great. They are optimizations for keeping middle management employed. The most obvious example being the size of the organizations themselves, which I think is much more often the result of benefits that accrue to the hiring manager for having more reports than any actual relationship with capacity, ability, or velocity. The qualities that make a good engineer are often the same ones that create a good engineering organization. Both start with deep understanding as the basis for innovation, cultivating the curiosity to look inside the black box. Both recognize that vision and engineering are often deeply intertwined and mutually informative rather than linear. The magic of both software and software organizations comes from those moments, where insight into how something works sparks entirely new ideas about what it could become. This is kind of outside the normal topic I would cover, but I do still like to talk about general software and general tech stuff and, I don't know, mix some in there in between. What do you think? Let me know your thoughts down below. Do you have some ideas about engineering that maybe people would agree with or disagree with? I would love to know. So if you liked the video, go like the video. And if you really like the video, go subscribe. And if you want to become one of these amazing people over here, check out the Patreon, Scribe, Stelly, Bearer Pay, linked in the description down below. That's gonna be it for me, and you wanna see some magic? Something like this.